Section 4, we now come on to expected value, variance, and standard deviation. Now, we've seen all this before when we were doing, when we did the previous few readings, and the expected value is just our weighted average. Yeah, now we said the weighted average, if we're looking at historic portfolio data, the calculation is the same as the expected value if we're looking to the future when we have a probability distribution. So the expected return on the portfolio return is the weighted average ERP. So expected return on the portfolio is the sum from I equals 1 to n, where you've got n different outcomes or n different components of the portfolio, WIERI. So although this has the possibility of getting very convoluted, let's say we have 4 different asset classes. So you've got 4 different components of the portfolio. So you've got 4 W's, W1, W2, W3, W4. They're the weightings. They add up to 1. And the ERI could be the basis of a probability function. So the probability of each one going up or down. So let's say the first weighting is equities. You may have different probabilities of different results for equities. And so ERI is a weighted average. And then you've got the weighted average for the overall portfolio. Now, that's a lot of work, and you would only get that in a very simple scenario, typically with a portfolio with 2 asset classes, say equity and fixed income, and each of those having 2 possible outcomes. So it's never going to get too complex. Each RI could be itself a weighted average, as I've described. The variance and standard deviation, look at the variance. It looks a bit complicated because you've got lots of brackets there, but in fact it's exactly what we've seen before. It's the expected square deviation. When we did this in the previous reading, we said the variance is the average square deviation from the mean. It's the mean square deviation from the mean. Here, it's the same thing. It's the expected deviation from the mean. The difference is, here you may be given probabilities, there may be weightings, and we'll see how this looks. So let's calculate the variance of earnings per share in the earlier example. What you've got in this table, we've worked it through, and this is a lot of work for one question. However, you need to be prepared for it. This is probably the extreme of how much effort is involved in getting a question right. But we're going to use the EPS example previously. You've got 4 probabilities. Remember, we came up with 4 mutually exclusive and exhaustive outcomes, where EPS is $1.20, 0.9, 1.8, and 1.5. You've got 4 probabilities shown in the table, 0.8, 0.32, 0.45, 0.15. Your mean, we worked out, well, the expected value was 1.4190. And so for each of these, what is the earnings per share minus the expected earnings per share? So for the first example, EPS is $1.20. $1.20 minus $1.419 is minus 0.219, and that gives us the third column here. Now, copy-paste the formula for the other 3. Yes, it's a lot of work, but in the exam, you'd probably have fewer outcomes than this, but you definitely have fewer outcomes than this, and the numbers would probably be nicer and more round to make life a bit easier. So we have 4 rows here. EPS minus expected EPS, you've got 4 outcomes there. We now square it. We want to find the average square deviation. So the 4th column, EPS minus expected EPS squared. So minus 0.2190 squared gives us 0.0480. And then for the other 3 as well. And then you say it's a weighted average. What's the expected value of the square deviation from the mean? So instead of saying this is some really complex, horrible formula, if you have got to the point where we know the expected value and we know EPS minus the variable minus the expected variable squared, now it's a weighted average of those 4. The variance is a weighted average of the square deviations from the mean. As I said before, it's the mean square deviation, so the expected square deviation. We're going to have, so EPS minus expected EPS squared is going to be 0.0480 with probability 0.08. It's going to be 0.2694 with probability 0.32. Multiply them across, so 0.4048 times 0.08 gives us 0.0038. 0.2694 times 0.32 at the second row gives us 0.0862, and so on for third and fourth. Add them up, and there's your variance. Now, I'm not going to say that's easy to do in a 90-second question, but I am going to say it's an extension of what we already know. We know how to do variances in general, where you have discrete outcomes, all with, so when we said here's the variance of 5 levels of return, you're just treating each one, you've got 5 different numbers, and you're adding up the square deviations, dividing by 5, or 4 if it's sample. Here, it's a bit more involved because instead of just adding them up, you've got probabilities involved. So if we do this 100 times, on average, 8 of them, EPS minus expected EPS squared is going to be 0.0480 8 times. The next one down 32 times, then 45 and 15. So it's a lot of work, but that's given us the variance of 0.1563. Why? So what have we, is this the population variance or the sample variance? Quick question. Now, what you need to understand is when I said we have 100, how do we get to the n? I made it up. Your probabilities add up to 1, not 100. And so when we talk about expected values or probabilities, then you're always going to be using your sigma and not your S. Your variance is the population variance. Your sigma is the, so your standard deviation is the population standard deviation. And that's simply because we haven't got an n. The n doesn't really mean anything here. N, if anything, is 1. So you certainly can't divide by n minus 1. There is a method we can use on the calculator, which is as follows. We can put the EPS in as our x coordinates on the data function, and the probability as the y coordinates. So let me go through that. And if this question does come up, then hopefully we can get there a bit more quickly. So calculator's up and ready. Press second data. And as always, press second clear work. Now we're going to type in the variable into the x and the frequency, or in this case the probability, into the y. Don't forget the probability needs to be whole numbers. So x01 is going to be 1.2. Enter. Probability times 100 is going to be 8. x02 is going to be 0.9. y02 is going to be 32.